Hi everyone. We're about to talk about the first type of faster sort, which is my personal favorite sort. I remember when I learned about these sorts a very long time ago, I didn't do a very good job at it. And then one day it clicked for me. I don't remember when it was. It was probably years later, to be fair. But I was like, oh my god, this is so cool. So this is my favorite sort. Personally, but I'd love to see what your preferences are for these things. So what we're talking about today is merge sort. Why? Sorry, I just want it to be correct. Merge sort. Sounds really funny, doesn't it? Merge sort. That doesn't make any sense. Why do we care about merge sort? Because we need some algorithms to be better than ON squared. We need them to be merge sort get. Yes, merge sort get gets that for us. Merge sort gets us an O n log n time. And that's really good because you think, oh, O log n. You think, oh, n squared, that's not too bad. Well, you know what? N squared for 1,000 elements is 1,000,000 steps. Whereas you look at n log n for 1,000 elements. What's log n of 1,000? Let's just base 2. What's log 2 of 1,000? It's probably like 15 or something. 10. Close enough. Within a factor. That gives you 15 times 1,000, which is just 15,000. That's substantially quicker. 15,000 divided by 1,000,000 is 1% of the time. 1.5% of the time. It is 99-ish, 70% quicker or something. Merge sort get. Merge sort get. Yeah. We like merge sort. We like things that are ON log n, right? N log n. That's the kind of sorting algorithms we're dealing with. So what do merge sort get? We will talk about what merge sort gets. So firstly, an overview of merge sort. Probably the most important thing to understand about merge sort, and a lot of this will carry through to tomorrow, is that merge sort, like quicksort tomorrow, they are both recursive divide and conquer algorithms. Okay, they both use recursion as a way of splitting up and subdividing it. Now you should already be familiar with this concept from binary trees, where you understand that you can think of a tree as a series of two halves, and then you can apply the exact same principle to both of those two halves, and you can just keep doing that. You can just keep breaking the same rule and applying it across a recursively, more and more divided space of items. The high-level understanding of merge sort is that you have a giant unsorted list of numbers. You break them into two halves. You apply merge sort to both of those, which sorts both halves, and then you can merge those two sorted halves back together. Okay? Now, to me that didn't make a lot of sense when I was first told it, so I don't expect that to be a groundbreaking idea for you. The big question about merge sort is how does it even take this and sort it at all, which we'll kind of get to in a sec. So it's like, the idea of merge sort, though, is that you are essentially, this is probably a more useful diagram, is you are essentially taking a list, say, of 8 items, you are breaking it into 2 parts, and then you're breaking those 2 parts into 2 parts, and then you're breaking those 2 parts into 2 parts, until you essentially get left with all of these numbers separately. So if you imagine that, we have this list of 8 items, we break it into half, we break that half into half, this half into half, we get left with this. That is all of the splitting and dividing stage of merge sort. The next step, though, is to merge them back together. So essentially, if you want to take a 5 and a 2 here, and you want to merge those back together, you recombine them, but now it's sorted. So you see here how it wasn't sorted, and now this one is sorted. It's a 2 and 2 and 5 sorted. You take this 4 and 7, which was sorted before, and you sort it, and it's sorted. This is still sorted, and then 2 and 6 are still sorted, right? You just keep applying that. So like, what did we do in this step here? We took 2 lists of one element, and we combined them together such that they're sorted. We took two lists of one element and we combined them together such that they're sorted. What we're doing here now is we're taking two lists of two elements and we're combining them together such that they're sorted. So I got my 2, 5, 4, and 7, and I combined those back together to get 2, 4, 5, 7. And then I can do the exact same thing over here. So I can combine my 1 and my 3, my 2 and my 6 to get 1, 2, 3, 6. And then I can take my two lists of four elements, 2, 4, 5, 7, and 1, 2, 3, 6, and I can combine them back into a sorted list, which gets me 1, 2, 2, 3, 4, 5, 6, 7. Ian says, what if it's an odd number array? I won't get into that much right now, but if it's an odd number array, just at some point here, you have a list of 3 that gets split into 2 and 1, and then the 1 just carries itself down. It's all the same algorithm. It's just a slightly more thoughtful way you have to code, but it's all pretty much the same. Yeah. So that's it, and merge sort's made up of 2 key steps, which is the splitting and dividing and the remerging. So the merging is why it's called merge sort, and the reason we referred to it as a recursive divide and conquer is because any kind of divide and conquer algorithm is about breaking a problem down into smaller and smaller and smaller components, solving those and building it back up again. So you can kind of see here, we're taking a big list, we're not trying to sort this list as if it's one list, we're turning it into 2 smaller lists, which we eventually sort down here. And by doing this, we can break the problem down into more manageable chunks. Now, let me also, so, okay. Looking at this, I guess some questions I have for you all are, conceptually, does this make sense? And what questions does this raise for you? So I'll give you an example. The one question I have when I first look at this always is, all right, but it sounds very complicated to just randomly take 2 lists and sort them together. Like, you know, hey, merge sort, you're making this sound like you're doing something genius here, but it's like, I can randomly break up my array into bunches of pieces and then force them back together again. The reason we're using merge sort is because it's apparently quick. Right, it's apparently quick, but this looks complicated. It looks complicated to merge these things back together. Yeah, like how do we get the n log n? Where is that? Like, I feel like I'm just sorting stuff anyway. So isn't this just going to be n squared in the end after some fancy splitting and stuff? The key thing to merge sort, I think, in my opinion, like the most fundamental thing to understand is that when you combine 2 sorted lists, the cost of combining 2 sorted lists is on. And that's a really, really kind of fundamental thing to understand, because if I have 2 lists like this, so firstly, if I just said to you, okay, I've got 2 lists of numbers. I got 5, 9, 8, 3, and then over here I have like 2, 8, 7, 6. And I just said to you, combine them together, right? Merge them together in a sorted order. That's going to be n squared. Because the only real feasible way to do that is to just combine them and run like a bubble sort or something on them. Because they're all just unsorted numbers. It doesn't matter that we've split them in half. Like, combining and merging 2 unsorted lists is just hard. It's just hard. What's key about merge sort is that when you're combining 2 sorted lists of numbers, like this, combining them is actually really easy because you can follow a fairly straightforward process whereby you essentially keep track of the smallest number in both of these lists. And there's actually an n-time algorithm, an on-time algorithm that helps you combine these effectively. And if I want to combine them effectively, what I do is I go and get 2 pointers or indexes, whatever you want to think of it as, to the first 2 elements, and I say, okay, which one's smaller? Which one's smaller here? It's the 1. Okay, so I go and write my 1 down here, right? And then I've done the 1. So then I move this little index thing across to the 2. Okay, and which one's smaller here? Well, they're both the same, but I'll move this 2 down. So then I move my little indexy thing across to the, I move my little indexy thing across to the 4. Which one's smaller out of the 2 and the 4? Well, it's the 2. So this particular like really simple approach can't be done on 2 lists that are unsorted. Which one's smaller here, the 4 or the 3? It's the 3, obviously. That's a 3. We move this one across. Then we say, is it the 4 or the 5? It's the 4. We're obviously going to move that across to the 5. I'll just do those in one sweep to save the pain. And then we get to here and we say which one's smaller, the 6 or the 7. And we put the 6 in, and then this is empty, and if one of the lists become empty, you just dump the rest of the other ones on. So I just move this to a 7 now. And what's really interesting about this process is that only took us n steps. There were 8 numbers there, and to merge 2 sorted lists only took us... To merge 2 sorted lists that had a total of 8 numbers took us 8 steps on the computer. It took us 8 comparisons, 8 steps. So the actual merging process is O(n), because the key thing again is that you're merging 2 sorted lists. And if you go back to our merge sort diagram, you can actually see this here. When we merge 2 and 5 and 4 and 7, they're both sorted. Right? So therefore it becomes, this was an n time operation. It took us 4 steps. This took us 4 steps. And then to merge these 2 together took us 8 steps. So before we look at the code, I might actually just say ahead to another diagram. I copy and pasted this diagram and then talked about the time complexity of it, which might be worth talking to, which is on the performance of this. So let's not even think about the code for a second, but how this works, roughly, is that if we take this and we just dump it in Paint again, nope. Okay. If we dump it here, the actual steps here, like splitting arrays is not an operation, right? It's kind of an operation, but basically, like each of these steps was like one step to like split it, and therefore this thing here is log n. Now, what do we know? What's log 2 of 8? It's 3. That makes sense, and this is true for binary search as well that we've seen. It's like when you take a list like 8 items and you just subdivide it, you do exactly log n steps. So I've got 8 items. It took me 3 steps to break this up. We weren't operating on this. We're just breaking it up. Most of the complexity of a merge sort happens during the merge, because you have to take 2 elements here and combine them together, which takes 2 steps, and then you have to take 2 elements and combine them together. So these 4 operations here take 2 steps, because what did we say before? You know, to merge 2 sorted lists together, the number of operations you need is the number of elements in both lists. So how do I combine these 2 lists of 2 together? Well, that takes 4 steps, because there's 4 elements between the lists. And then when I combine the 2 lists of 4 together, that takes 8 steps. And what do you notice is that at each part of the merge, this took us 8 steps, this took us 8 steps, and then this took us 8 steps. How many times did we have to do those 8 steps? 3. And that's where we get basically that the cost of merging this fully split up list is n log n, because we had to do 8, which is the size of the list, exactly 3 times, which is the log n. And that's where we end up with that complexity. Now, splitting it up, you could kind of ignore this component if you wanted to. You could call it 3, whatever. Like, there's different ways of thinking about this, but the point is this is easy. This is really easy stuff to do. So this is where all the complexity actually happens. And that's how it ends up being n log n, because the idea is that by dividing it up and breaking it into a series of smaller components, it's a lot easier to kind of rebuild this in a sorted way. The one downside of a merge sort is that it requires extra memory, which is something we didn't see in the in like the previous example. In like the bubble sort, insertion sort, selection sorts, they were all in place sorting algorithms, whereas a merge sort actually requires more memory, because you can't really like swap things in place here. It's just like the nature of the algorithm. So you basically have to get like your starting array, and then you create like your temporary array here that you do your work in, and then when you're done you can copy it back to the start if you'd like to. But that's one downside of merge sort, is that you do need extra memory. Yeah, so someone said why is it better? It's because it's n log n in the worst case. So for massive data sets, like 1 million items, merge sorts are great, I guess. Yeah, because, you know, it's much faster. Like 1 million squared is a lot, right? It's just thinking about it. It's like doing a bubble sort on a million items would probably take the best part of like a computer, maybe like 2 hours, I would guess. A merge sort would take, I don't know, tenth of a second, something around that. Like it would take whatever the log of a million is times by a million. Like the log of a million is 12. I don't know. It's log base 2. It's quick, right? Like this is why we talk about big O notation and stuff. It's fast. So it's much faster. That's kind of how it works though. Another good diagram that you can find on the internet, the interwebs, for merge sort, which is actually one that helped me understand it the most. I have a memory of this one, is this diagram. I think this one helps explain the divide and conquer part. So you can see here it splits it into halves, splits that into halves. So it's doing this recursively, right? So it splits everything into halves until it gets down to single elements, and then it starts merging those elements back together. Because each of these two lists that it's merging are sorted, it can do it really quickly. You'll notice there's only actually ever like n movements here. So like, you know, we're at 6 and then 7 and 8. So to kind of recombine each layer takes exactly n steps. So 2 steps, 3 steps, 4 steps like this, right? And the exact same thing. So that's what I meant before about each time we do these like progressive merges, it's just an n time operation. And the power of merge sort is that we only have to merge it log n times. So same thing here, and then we end up with everything merged again. I'll just let this finish for completeness. But the other thing you'll see is that once one list runs empty, it just kind of dumps the other list on the end. Like it's just like, oh, we're done, let's just get everything on it now. Caleb says, so each merge is a mini sort then? I guess so. I don't really know how much I'd want to call like merging 2 sorted lists a sort, but I guess it's a sort. It's not a sort in the same way that we've dealt with it previously, right? Like it's not like an algorithm that can just take any, like it's quite constrained in its input. The merging function requires the 2 lists it's merging to be sorted. So yeah, it is a sort in the sense that it takes 2 sorted lists and it turns it into one big sorted list. Merge sort linked list exam question confirmed. I don't even know what that would look like. I don't know to what extent that would make any sense. Yeah. Okay, so there's like the merge sort. We can look at the code though. Like, I mean, we can look at the code last because I actually think the code can be confusing. But so we mentioned before that merge sort has a best and worst case complexity of n log n. It's probably by far the most time efficient sorting algorithm that we talk about in this course. The one thing to be wary of is that it's not an adaptive algorithm though. It actually takes the exact same amount of time on a sorted list as an unsorted list, because merge sort is kind of a bit dumb. It's not really looking for minimums. It's not really doing anything like that. It's literally just saying, I'm going to break this all up and then bring it back together. And it doesn't care whether it's in order or whether it's not in order. It'll just do it. So fast, non-adaptive, and I like that about merge sort, because I think, you know, it just makes it conceptually really easy, because you're just like, here's the process, do the process. I don't care what the numbers are, just do the damn thing. So we do need extra memory though. That's one of the downsides. Oh, you can do merge sort on linked list. Sorry, I forgot. My bad. I put that in like on the weekend, so I just think I was mixing that up. Now, how does the merge sort algorithm work? Well, at a high level, you can understand merge sort as you have a list of numbers and you call merge sort on them, just like a normal sort. Imagine this just says sort number. It's the same as all the other sorts. You can see though that the algorithm essentially, what it does is it takes your array, it finds the midpoint of that array, and then it recursively, just like a binary tree, calls a sort on the left-hand side. It calls itself on the left-hand side and the right-hand side. So this is the left-hand side because it's from the left index to the middle, and then the right-hand side's from the middle to the right index. Now, I want you to try and like think about the binary tree weeks we did, because we talked a bit about in order, post order, pre-order, and a good way to think about how this algorithm works is that the merging happens postfix, post order, whatever, in the sense that, remember what we said about like postfix stuff was that the idea with like doing postfix printing with a binary tree is that you explore as deep as you can and then you do your operation. Prefix was you do your operation before exploring. In order, infix was like doing your operation between exploring both sides, and then postfix, post order, was doing it after. So the idea here is that we want to fully expand the left and right trees before we merge it. And that's consistent with what we've seen on this too, where it's like we actually do all the expansions before we do the mergings, essentially. Well, I don't want to say we do all the expansions. You expand your section as far as you can, and then you merge it back together. So we split, and then we end up merging it all back together. And this is kind of called recursively on itself. So the actual merge sort algorithm is quite straightforward. The merge function, though, is a bit more complicated. And what you have to think of this merge function as is, it's what I said before. This is a function to take in two lists, two sorted lists, and merge them back together. The only difference here is that these sorted lists are assumed to be like contiguous in memory. So like in reality, when we say two sorted lists, what we're saying is that we've got this big chunk of numbers here like this. Say it's like 3, and we've got like, 1, 5, 6, 2, 4, 7. Where like this is the memory we're trying to sort, but clearly like this is the middle, this is the high, and then this is the low. So like, can you please merge between here and here and here and here into a new list like this? And then that's when it takes that and it goes, yep, I'm going to go 1 and then 2 and then 4 and then 5 and then 6 and then 7. And then it copies it back into that after it's done that. And you can see this kind of here, right, is we have to create our new list, the temporary list. That's the extra memory. We then saw this loop stuff here. This is kind of going through. Remember how I did that thing with the little arrows and it was like, oh, move that one down and then we'll move this across and then we'll move this across. Like, that's what that bit is here. It's going through each like sorted list and figuring out which one to move down. And then once you've finished either of the lists, this is you saying copy the rest into it. Just copy all the rest down there for us. And then this is the copying from the temp array back up to this array. So that's like finally, we're done with the temporary array. Let's copy it all back and delete our temporary array and then move on. It looks like a lot of code and it looks like a lot of indexes, but logically it's relatively straightforward. If you can draw it out, it's pretty okay. It's a good question. So Trent says, how does the K++ in square brackets work? So the way that ++ works is that if like, we can show you, probably is the easiest thing. I'm going to have my main function just like not do anything. So if I have an array like this, and then I say like int I equals 0, and then I say printf %d a of I++. Let's do that a few times, right? What actually happens here is that when you say I++, like we all know what I++ does, it increments I by 1. But in this case here, what happens is that I increments, and what I++ actually returns, think of I++ like a function call, what it actually returns is the value of I before you incremented it. So I at this point is 0. We increment it to 1, but what this statement actually turns into is 0 once it's done. So it's like, I'm going to increment I from 0 to 1, and I'm going to return 0. And then this one, when I is 1, says I'm currently 1, I'm going to increment myself to 2, but I'm going to give you what I was before I incremented it, which was 1. And then that's what it ends up being. So in this case here, in these algorithms, it's pretty much the same thing. It's like we could obviously split these out a bit. So if I just copy and paste this, you could probably make this potentially. I was doing that thing I don't like. Oh no, that's okay. I'll just copy a little bit of it. You could split this out actually by saying like you could do this if you want to as well. This is like these are the same things as what's there. It's just some people would consider it more concise, which I think they're probably right. It's a lot easier to read that, especially when you're dealing with loops and you're like, all right, each time I access this, I'm incrementing it. I'd never want to see it again. But the merge thing is one of those things that you really just got to sit down and play with and look at. You know, so I can't go through this here in excessive depth for you, but but yeah, I mean, you can play with this, you can reason with it. It actually states the logic really clearly. It's like scan through both until one of them's empty, dump the rest of them in, copy from the temp array back to the main one. Yeah, so when it says, what does it mean by copy items from unfinished segments? Do you remember how with the merge sort, when they were merging them back together, sometimes you've kind of moved everything down from one side, but the other one's like not done yet. So you'll actually see it here when we merge 5, 6, 1, and 3. So when we're merging them both, we're looking at this while section. So this while section here is what's happening now. But once we've moved one whole side in, we're suddenly going into this copy from unfinished segment part. And the same thing here. So it's like, this is the while loop, the bigger while loop, and now it's like done, and now we're just copying and everything else. Because once one side's gone, you don't need to check anything anymore. Like, you know the other side's sorted. So you can just like drag it all down, which is nice and easy. Last thing, which we're gonna look at tomorrow again, but there's these, you've seen this, some of you have seen this, some of you, your tutors have pushed this onto you already, some of you whatever. I'm really glad I'm not logged in on my account. I always get weird about people seeing my recommendations. So tomorrow we're going to talk about quicksort and go into a bit more about how these things are visualized. There's a lot of people who like looking at, oh my god, I can't remember this thing. It hurts me personally, so I'm not going to show you the folk dancing. It's slow and I hate the music and it makes me want to scream. Though I'm sure one of your tutors likes it and they get to show you, so they can do that for you. Though the more interesting ones for me are definitely looking at these things. This is not something profound. Everyone knows about these things, but these are cool because you get to see. I might make this not full screen so you can see the title here, but these are great ways to visualize some of the sorts that we've looked at. I just want to see if my desktop audio is on, or it's not. But audio output capture. Oh, I muted it. One sec. So I mean, the sound's horrible. I just want to give you a little bit. Too much. Yeah, so like for instance, I just want to like really quickly show you just a few we've looked at today because I don't want to finish up late. This is like a selection sort, right? And if you kind of pay attention to this one, you see all these little flashes of red here. That's it doing sweeps through this list and finding the smallest item and swapping it at the front. If you pay attention to this closely, you'll notice that random elements here get swapped. You'll just see random spikes changing. That's what happens as it's swapping. And you'll see the same things with like insertion sort too. You can see the easy like moving it back. This is a great way to visualize things at a high level, because this is effectively what happens with sorts like insertion sort, right? Is you grab each element and you're reshifting the array every single time. And then you see the same thing for bubble sort, which is swapping. There's a whole bunch in here. Some of them even I don't understand very well. I think bubble sort might even be near the end. But merge sort's, one of the more interesting ones. You can actually get a sense here of how Merge sort is divide and conquer, is it's basically breaking everything down into chunks and then merging them back together. And again, if you watch this a few times, you'll start to get the intuitive understanding of what's happening. Because every time you see those two big lists, that's it sorting those two, that's it merging those two sorted lists together. So it's all the breaking down and just merging sorted lists after sorted lists, and so forth. So, and this one's n log n as opposed to all the other sorts. So we'll talk about one sort tomorrow, which is quicksort, and we'll revisit some of these maybe in a bit more detail. We definitely don't talk about everything in this course. Though I was hoping, I wonder if there's bubble sort. I can't remember if there's bubble sort in this. They're never in the order I expect them to be in naturally. Shell sort. We're running out of time. There we go. Bubble sort. Yay. Yeah, you'll see bubble sort. It's just shifting things. You can also see the general trend of bubble sort is that it's in effect just moving the highest value up to the top. Like when we say swapping, it's basically just like swapping and shifting all the way up the top. But you know, and you can see again bubble sort. If you design it properly, it can also, like the ones we have in the lecture slides, speed up as you approach the end of it. See how it's speeding up because it's having to look through less items? Yep. Anyway, yeah, I'll talk to Kevin about how much we're going to talk about with assignment 1. I have to talk to him about some stuff tonight, but we'll figure that out in a week or so. Anyway, it's 4 o'clock, so I'm going to wrap up. If you could please do the standard feedback thing. We'll talk about quicksort tomorrow. We'll talk about assignment 2, part 3 tomorrow. I doubt we'll use... Sorry, every time I say tomorrow, I mean Thursday. This is like the first term in a long term I've had lectures that aren't on adjacent days, so I'm sorry for whenever I say that. And it probably won't be the full 2 hours, but yeah. Thanks, everyone, and I hope you have a great day, and I'll see you on Thursday, and be happy as you can. At least try to be. So, see ya.